Okay. So, next we will start that first order circuit. This is your chapter 6, right. So, here we will see the DC transient, particularly the your RL circuit and RC circuit. Only we will see that why it is called first order circuit also. So, when this topic is over, we will go for the AC circuit. So, we start for single phase, then 3 phase, right. So, first some introduction I have made it for you, that in the previous chapters we have considered 3 passive elements, the resistors, capacitors and inductors individually. So, in this chapter we will examine your 2 types of circuit, a circuit your comprising a resistor and capacitor, and a circuit comprising a resistor and your inductor. I mean, we will see the 2 types of circuit, that is a circuit comprising a resistor and capacitor, and we will see a circuit comprising a resistor and inductor, and these are called RC circuit and RL circuit respectively, right. We carry out the analysis of RC and RL circuit by using your what you call KCL, your KCL and KVL, and produces different equations which are more difficult to solve than algebraic equation, right. So, just let me this thing. So, the differential equations resulting from analyzing RC and RL circuit, that is your the differential equation resulting analyzing that RC and RL circuits are of the first order, right. Hence, it is underlined the circuits are known as first order circuits. A first order circuit is characterized by first order differential equation. So, there are 2 ways, it will be 2, right, I am correcting it, right. So, there are 2 ways to excite the circuit. The first way to excite the circuit is by initial condition of the storage element, right, that will be a source free circuit, right. These circuits are called source free circuit, that means circuit is excited by the initial your what you call that your conditions of the storage elements, and these circuits are called source free circuit, right. So, actually in that case we assume that the energy is initially stored in that your what you call in that circuit element, just one in that is stored in the capacitor or inductive element, right. So, the stored energy causes the current to flow in the circuit and gradually dissipated in the resistor. So, source free circuits are free of independent sources, but they may have dependent sources. So, it may have I mean it is there will be no independent sources, but they may have dependent sources. The second way to excite the first order circuit is by independent sources. So, in this chapter or in this topic we will consider DC independent sources, right. First we will see the source free circuit. So, whenever you see source free circuit, here when we will see when I will solve numericals 1 or 2 cases or 2-3 cases, I will tell you the solution and this way, but your 1 or 2 cases I will not tell you that how 1 or 2 cases I have obtained. I will give you your what you call that you think that how it has come, but that will come later. So, when DC source of a RC circuit is suddenly disconnected, a source free RC circuit occurs, right. So, the energy already stored in the capacitor is gradually dissipated in the resistor. So, that means figure 1 suppose it shows a series combination of a resistor and an initial energy your charge initially charged capacitor. So, main objective is to examine the circuit response. So, in this case this capacitor was initially charged and one resistor is there. Although IC and IR it is a simple circuit, but at this point if you apply KCL, if you take like this, that IC is going this way and IR is going this way, both are leaving. So, IC plus IR equal to 0, right. Although it is the same circuit, but for some analysis we will do that, and this is your this side is your voltage, right. This is the voltage. So, V is the voltage across the capacitor or across the resistor, it is same, right. So, it is a source free circuit, there is no independent source in the circuit, assuming that this capacitor was initially charged, and if you apply KVL at this point, it will be IC plus IR is equal to 0, right. So, this is a source free circuit. Now, So, assume that the voltage across capacitor is V t. Since the capacitor is initially charged, we assume that at time t is equal to 0, the initial voltage V 0 is equal to V 0, right. So, in this case we are assuming at t is equal to 0, that is V 0 is equal to your capital V suffix 0, this is the voltage, initial voltage. Now, store energy in the capacitor initially, the W C 0 is equal to half C V 0 square, right. Just hold on. So, just hold on. So, in this case the store energy in the capacitor is this W C 0 is equal to half C V 0 square, right. So, applying KCL at node A, I told you I C plus I R is equal to 0, right. So, let me clear it. So, by definition we know that I C is equal to C into dV by dt, and at the same time I R is equal to V by R. If you come to this circuit, that your this voltage I told you, this voltage is your V. So, I R is equal to V upon R, right, because same voltage across the capacitor and across the resistor. So, V is equal to I R. So, I R R into I R. So, I R is equal to V by R. Similarly, here also your I C is equal to C into dV by dt, right. This V is across the same, this capacitor as well as the resistor. So, let me clear it. So, in this case your this is C into dV by dt plus V by R is equal to 0, because I R is equal to V by R is equal to 0, or dV by dt plus V by R C is equal to 0. So, this is a first order differential equation, since only the first derivative of V is involved. So, equation 4 can be written as, we can write dV by V is equal to minus 1 upon R C dt. So, this one you can write that your dV by V is equal to minus 1 upon R C dt. This is equation 5. Integrate both sides, this side you will get ln V natural log minus T upon R C plus some constant ln A we have taken, instead of A or C1 C2 directly we have taken ln A for simplicity. So, this is equation 6. Now, where A is the integration constant, thus ln, if you make this one ln V, bring this one to this side, left side, minus ln A, right, is equal to minus T upon R C. So, this side can be written as ln V upon A is equal to minus T upon R C, that is what it is written here, right. So, this is equation 7. So, let me clear it. So, taking power of E, now if you take power of E, it is given. So, V t is equal to A into your e to the power minus T upon R C. Actually, it was given here, no? Here it was given here, right. So, here here it is given, ln means it is log of base E. So, V upon A is equal to e to the power minus T upon R C, or V is equal to A into e to the power minus T upon R C, as V is a function of T, that is why we are writing V t, right. So, just so that is why we are writing V t is equal to A e to the power minus T upon R C. Now, but from the initial condition, when the time t is equal to 0, V t is equal to V 0 is equal to capital V suffix 0, right. Therefore, at t is equal to 0, if you write, then it will become, this part will become 1 and it will V 0 is equal to A. So, that is A is equal to V 0, right, because V 0 is equal to, earlier we are writing V in initial condition, V 0 is equal to capital V suffix 0. So, this is equation 9, I have not given some equation number. Therefore, my V t is equal to V 0 e to the power minus T upon R C, this is equation 10. Now, equation 10 shows that the voltage response of the RC circuit is an what you call is an exponential decay of the initial voltage, and it is called the natural response of the circuit, because it is given e to the power minus T upon R C. So, naturally it is an exponential decay of the initial response, and it is called the natural response of the circuit. because this response is due to the initial energy stored and the physical characteristic of the circuit and not due to the external voltage or current source, right. That means, this is called your natural response of the circuit, because the response is due to the initial energies stored and the physical characteristic of the circuit, right, and not due to some external voltage or current source, because it is a source free circuit. So, this is called the natural response, right, of the circuit. So, let me clear it. So, now if we plot that V is equal to V 0 e to the power minus t upon tau, that is your that is V is equal to your V 0 e to the power minus t upon R c. If we take tau is equal to R c, then V is equal to V 0 e to the power minus t upon tau, where tau is equal to R c. Tau actually is called the your time constant, right. We will see that. So, that is why this plot is V 0 is equal to the power minus t upon tau. Now, let me clear it. So, voltage response, this is the voltage response of the RC circuit now, and when I will come to that, but I am telling that when t equal to tau, when t is equal to tau, then V will be is equal to V 0 e to the power minus tau by tau, that is V 0 e to the power minus 1, that will become 0.368 V 0, that is here it is written here. When t is equal to tau, then it is 0.368 V 0, right. So, let me clear it. Now, I will come to some explanation. So, this is your figure 2, this is your figure 2. Figure 2 shows the natural response at t is equal to 0, we have the correct initial condition V 0, your what you call your V is equal to V 0, at t is equal to 0. So, it is V is equal to V 0, right, and as time t increases, the voltage decreases towards 0. The rapidity with which the voltage decreases is expressed in terms of the time constant denoted by tau, right, and expressed as tau is equal to R c. This is the time constant of that circuit. Therefore, equation 10 can be expressed as V t is equal to V 0 to the power minus t upon tau, I told you. So, at t is equal to tau, V tau is equal to V 0 e to the power minus 1, that also I told you, is equal to 0.368 V 0, that means this one 0.368 V 0, right. So, that means equation 13 we can state that the time constant of a circuit is the time required for the response to decay 36.8% of its initial value. This is 0.368, that means if you take in percentage, that is 36.8% of initial value means V 0, right. We can state that the time constant of a circuit is the time required for the response to decay 36.8% of its initial value. Now, I have make a table 1 shows the value of V t by V 0 from table 1. It is seen that the voltage V t is less than 1% of V 0 after t is equal to 5 tau. I mean, this is V is equal to V t is equal to V 0 to the power minus t upon tau, that means V t by V 0 is equal to the power minus t upon tau. When t is equal to tau, its ratio is becoming 0.3678, when 2 tau 0.1353 and so on, up to when 5 tau it is 0.0067, less than 1%, right, less than 1%. Therefore, that when after t is equal to 5 tau, right, it is less than 1%, thus it is your what we call customary to assume that the capacitor is fully discharged, right, fully discharged or fully charged when it will be in other way, right, after 5 time constant. In other words, it takes t is equal to 5 tau for the circuit to reach its steady state when no changes take place with time. That means, for this graph, if you go up to tau, 2 tau, 3 tau, up to 5 tau, so time is equal to t is equal to 5 tau, after that you will find almost no change, right, it is almost reached the steady state. So, that is your what you call this table shows, that this table shows, right. So, the time constant may be viewed from another perspective. Evaluating the derivative of V t in equation 12 at t is equal to 0. So, equation 12, if you come to this equation 12, this is your equation 12, V t is equal to V 0 e to the power minus t upon tau, right. Take the derivative of this, right. I will come to that. You take you take V by V 0, then e to the power minus t by tau, right. So, ddt of V by V 0 you take at t is equal to 0, it becomes minus 1 by tau e to the power minus t upon tau, and at t is equal to 0, right, it becomes minus 1 upon tau, right. So, this is equation 14, say. Now, from equation 14 we can state that the time constant is the initial rate of decay or the time taken for V by V 0 to decay from unity to 0, assuming a constant rate of decay. This initial slope at t is equal to 0, your what you call interpretation of the time constant is used in the laboratory to determine tau graphically from the response curve displayed on an, say, oscilloscope, right. So, for determining tau from the response curve, draw the tangent to the curve at t is equal to 0. The tangent meets the time axis at t is equal to tau. That means, at t is equal to 0, at t is equal to 0, if you draw a tangent, it will meet here at tau, right. Here it will meet here at tau, right, and this tangent is at t is equal to your 0, somewhere from somewhere you draw the tangent and it will meet at tau, right. So, this is determination of time constant tau from the response curve. This way also you can find out your time constant at the laboratory, whatever graph you get, from that you can do it, and then 2 tau, 3 tau up to 5 tau it is shown, right. So, it can be observed from equation 11. If you come to equation 11, right, hold on, this is tau is equal to R c, right. So, it can be observed from equation 11 that the smaller the time constant, the faster the response. This is shown in figure 4. I mean, if this, when tau is equal to 2, response is slower, when tau is equal to 1, much faster than tau is equal to 2. If you further your tau decreases, response becomes faster, right. So, this side is taken, V upon V 0 is equal to the power minus t upon tau, the ratio is taken on the y axis. So, this is the response curve of various values of the time constant tau. At any rate, whether the time constant is small or large, the circuit reaches steady state at t is equal to 5 tau, because it is less than 1% that you are of your what you call the ratio, whatever you have taken, right. So, circuit reaches steady state at t is equal to 5 tau, right. Therefore, current I at t can be expressed as I at t is equal to V t upon R. We have seen in the circuit same thing. So, it will be V 0 upon R e to the power minus t by tau. This is the current I R, right. The power dissipated in the resistor is P t is equal to V t into I R. So, if you put V t is equal to your V 0 e to the power minus t upon tau and I R is equal to this one, this expression, equation 15, multiply, you will get V 0 square upon R e to the power minus 2 t upon tau. This is equation 16, right. So, the energy absorbed by the resistor up to time t, the W at t is 0 to t P t dt, right. P is a function of t. So, 0 to t, this is equation 16, V 0 square upon R e to the power minus 2 t upon tau dt, right. If you integrate this, you will get your tau is equal to R c, the time constant, half C v 0 square into 1 minus e to the power minus 2 t upon tau. Note that as t tends to infinity, omega r infinity is equal to half C v 0 square, that is omega c 0, right. So, initial energy stored in the capacitor is eventually dissipated in the resistor. So, if you t tends to infinity, then it is simply becoming half C v 0 square, because this term will not be there, and is equal to your initial energy stored W c 0, right. So, initial energy stored in the capacitor is eventually dissipated in the resistor. So, next we will take your 1 or 2 small some example. So, this is hope this source free RC circuit will be understandable to you, right. Actually, nothing is there, only very simple thing, right. So, here your a simple circuit of this thing is taken, a series parallel your parallel circuit, right. So, 5 ohm resistor is here, 0.1 microfarad capacitor is 0.1 farad is there, voltage across it is Vc, this 5 ohm resistor, and this is 15. 5 and 15 both are in series, but taken given separately, and current through is Ix, and voltage across 15 ohm resistor is Vx. You have to find out initial values of the your capacitor voltage, that is your 10 volt is given Vc0. We have to determine Vc, that is your this one, then Vx and Ix for t greater than 0. This we have to find it out, right. Now, first we obtain the equivalent of Thevenin resistance across the capacitor terminal. So, Thevenin resistance we have studied, right, Thevenin equivalent. So, in this case, if you try to find out your what you call that your across this these two terminal, what will be the Thevenin resistance, though this 5 ohm and 15 ohm, so 20 ohm. So, it is here both are in series. So, let us see it is equal to 20 ohm, that means, and 5 ohm, these two are in parallel. So, it will be 5 into 20 divided by 5 plus 20. So, it will be 4 ohm, right, 100 by 25. So, 4 ohm. So, let me clear it. So, if you find out R eq is equal to R Thevenin, it is 5 into 5 15 plus 5 and 5 plus 5 plus 15. So, same thing, that is your what you call 4 ohm, right. I little all these things I have written like this, right, but there I showed the calculation. Therefore, equivalent circuit will be this capacitor, it is a source free circuit. So, 0.1 farad, and this R eq is equal to 4. Remember, for this kind of thing you have to make the R Thevenin first equivalent, right. Let us see how things happen, and this voltage is V, that means across the 0.1 farad capacitor it is V, across R also it is your R eq also it is V, right. So, let me clear it. So, the time constant is tau is equal to, we have seen R c. So, it is R eq here into c. So, R eq is 4 into c is 0.1. So, 0.4 second, right, and V is equal to, you know, V0 e to the power minus t by tau, but V0 is given 10 volt. So, V0 is equal to V0 is equal to Vc0 is equal to 10 volt, it is given, and tau is equal to 0.4 second. Therefore, Vc is equal to V is equal to 10 e to the power minus t upon 0.4. So, that is 10 e to the power minus 2.5 t volts. This is simple thing. From the previously developed your formulas, we are just putting the data. So, from figure 6.5 we use the voltage division to get Vx, right. Now, if you come to this figure, so first suppose if this voltage is V, right, then voltage division, this is Vx. So, voltage division, because 5 and 15 ohm are in series, so it will be 15 by 15 plus 5 into this V, that will be your Vx. This voltage across this is V, so it will be 15 divided by 15 plus 5, because it is 15, here it is 5 into your this voltage V, that is voltage division, right. So, let me clear it. So, this is what we have done here. This is Vx is equal to 15 upon 15 plus. So, it will be V we have got 10 e to the power minus 2.5 t, V is equal to Vc, So, it is 0.75 into 10 e to the power minus 2.5 t. So, it is 7.5 e to the power minus 2.5 t volt, right, and Ix is equal to Vx upon 15, because across 15 ohm resistance the voltage is Vx. So, naturally we can take Ix is equal to Vx by 15. So, Vx we have got. So, Ix is equal to Vx upon 15. So, it will be 7.5 e to the power minus 2.5 t upon 15 is equal to 0.5 e to the power minus 2.5 t ampere. This is your Ix, right. This is the answer, all answers we have got. Now, next example. I hope you are understanding this. So, the initial voltages on the capacitors C1 and C2 in the circuit, I will show you, shown in figure 7, have been established by sources not shown, but initial conditions have been established. This is the language of the problem. The switch is closed at t is equal to 0. Therefore, you determine V1 to V2 to V1t, V2t, then Vt and It for t greater than 0, right. Sorry. Next, you calculate the initial energy stored in the capacitors C1 and C2, right. Next, C is determine how much energy is stored in the capacitor as t tends to infinity, and so that the stored energy delivered to the 250 kilo ohm resistor is the difference between the result obtained in B and C. So, these are the 4 things you have to make it, right. Now, here one thing I will not tell you, I will just this thing, but first this is the circuit is given and look at the polarity, right. So, here we have taken V1t, this is the capacitor C1, it is 5 microfarad, this is capacitor C2 20 microfarad, and this is plus minus, somewhere I have marked plus minus. So, this is V1 t, V2t, right. So, V1t means across C1, V2t means across C2, and this is 250 kilo ohm resistor, and across the voltage is Vt and current flowing through is It, and switch was charged, this capacitor was charged, but switch was opened. Now, switch is closed at t is equal to 0, right. So, question is look at the polarity here, this polarity is given plus, here it is minus, but here it is minus, here it is plus. This is your tricks in the problem. So, I will simply write it, and only one or two places I will tell you, look at this when you will solve this problem, you will see that the polarity of this whatever it is given, this is minus, this is plus, and again here it is plus, here it is minus. So, you can easily or what you call, you can easily make it that what is the initial conditions, right. So, let me clear it. So, all these things are given, I mean all this your what you call, this is given and you have to find out, right. So, now question is, and initial voltage here is given 4 volt and here it is 24 volt, right, but look at the polarity and accordingly you have to choose the sign of that your what you call that initial voltage. So, and so this polarity is marked. So, figure this actually these two capacitors are in series 5 microfarad and 20 C1 and C2. So, it is equivalent to the way you do the parallel resistor. So, therefore, here it is Ceq is equal to 1 upon C1 plus 1 upon C2 to the power minus 1 reciprocal, right. So, 1 upon 5 plus 1 upon 20 is reciprocal, it becomes 4 microfarad, that is C equivalent, and given that Vc10 just I am writing that 4 volt and Vc20 24 volt, right. So, this is the initial condition, therefore, Vceq will be Vc20 minus Vc10, that is 20 volt, because if you try to take your what you call this thing, suppose if I want to take Vceq equivalent, right, that is Vceq 0, suppose if I want, right, and if this is my plus and this is my minus. So, it will be Vceq, right, then minus your Vc20, then plus Vc10 is equal to 0, right. So, I am just looking at that polarity, that means Vceq is equal to Vc20 minus Vc10. So, it is given 24 volt, the Vc2 24 and that is given 4. So, it is 20 volt, right. So, this is that your what you call Vceq 0, suppose if you look like this, right. So, that is why that your Vceq 0 is equal to 20 volt and V0 is equal to then capital V0 for Vceq 0 is equal to 20 volt, because this is the equivalent circuit, so source free RC circuit whatever you have done, and this is 4 microfarad and this is here 250 kilo ohm, and same way we are drawing, this is Vt, this is the equivalent circuit of that one, right. Now, the time constant is tau is equal to Rcq, 250 into 10 to the power 3, it is kilo ohm. So, convert into ohm into 4 into 10 to the power minus 6, 4 microfarad. So, that is 1 second. Thus, the expression for Vt is, we know Vt is equal to V0 to the power minus t upon tau. So, it is 20 to the power minus t volt. So, It is equal to from this circuit simply Vt upon R, the earlier we have seen. So, it is 20 to the power minus t by 250 into 1000. So, 80 to the power minus t microampere, right. So, by definition we can calculate the expression for V1t and V2t. So, this we know V1t is equal to look at the polarity of V1 and V2, right, everything. So, just we have made it know that your what you call that IC plus IR is equal to 0, something we have given, no. So, or IC plus your what you call that your IT, instead of IR you can make it is IT, right. So, that means IC is equal to your this is a general thing, right. So, you have to find out V1 and V2, right, and this current IC is flowing through both your C1 and C2 both are in series. So, through both C1 and C2. So, what you have to do is just you have to see that how we write the equation, right. IT is given. So, this is your, just hold on, let me clear it, so, this if you come to this circuit, equivalent circuit, this is your IT, and this is, suppose this is my IC, right. Somewhere if you put the way we saw that IC plus then IT is equal to 0, right, or my IC is equal to minus IT, right. So, we know IC is equal to C into dV by dt in general. This is your what you call, this is your equivalent circuit, but if you come to your this circuit, original circuit, right, when C is closed, when the switch is closed, this is closed. So, this is IT and say this is current is flowing IC. So, here also IC is equal to then minus IT, because IC plus IT is equal to 0. This is closed, apply case some point at KCL, right. So, IC is equal to minus IT, right. So, that will be IC is equal to, one is your what you call that your C1 dV by dt, another will be dV1 by dt, another will be C2 dV by dt, separately you have to do it. So, if you come to now this expression, this equation, if you come to this equation, we are writing now, after you just do the integration. So, it will be minus 1 upon C1 0 to t, this IT expression is there, we have got this expression 8 to e to the power minus t microampere, right, and 0 to t, and this is we are making it minus 4, that is initial condition Vc0 is given 4 volt, but here we are putting minus 4. So, why we are writing minus 4, just this is your what you call a problem to you, you find out that why you are doing it, try to understand why you are doing it, right. Instead of plus 4, here it is minus 4, right, just try to understand this. So, this is a problem to you, right, and otherwise if you can't do it, we will answer in that forum, right, do not worry, but first you think. Then similarly, after simplifying this, V12 is equal to 16 to the power minus 2 minus 20 volt. Similarly, V2t is equal to, here same thing, that IT is there and your whatever capacitors value was there, everything is given there, right, everything is okay, but here we are putting that initial value V2 V0 24 volt, here it is plus sign, right, not minus sign, look at the polarity there and just think, right, why we have made it like this. So, that means if you do is V22 is equal to 4 e to the power minus t plus 20 volt, right. We also can obtain V22 by using KVL. If you apply KVL, Vt is equal to V1t plus V2t, or V2t is equal to Vt minus V1t. V2 you got 20 to the power minus t, therefore, V1t minus 16 to the power minus t plus 20. If you simplify, you will get the same thing, V2t is equal to 4 e to the power minus t plus 20 volt, right. Now, B part, the initial energy stored in C1. So, this question is given there, here it is minus 4 and here it is plus 24, initial voltage 4 volt, here is 24 volt, but this is a question to you, right. So, that second part is initial energy stored in C1, it is WC10 is equal to half C1 Vc10 square, you put all the values, you will get 40 microjoule. Similarly, for WC20, if you make half C2 Vc20 square, substitute all the values, right, you will get your 5760 microjoule, right. Now, total energy stored in the two capacitor, you add 40 microjoule plus 5760 microjoule. So, 5800 microjoule, right. Now, C, as t tends to infinity, V1 is equal to V1 infinity, you will get minus 20 volt as t tends to infinity, right, and V2 is equal to V2 infinity, you will get 20 volt, right. So, all V1, V2 expressions are there, just see that t tends to infinity how much it is. Therefore, the energy stored in the two capacitors is, that is Wc half is equal to half, that is your 5 plus 20 is 20 into 10 to the power minus 6 into 400. 400 means this 20 square, right. So, minus 20 square is 400, plus 20 square is also 400, right. So, and it is your half C1 plus C2, that is 25 microfarad actually, that is 25 into 10 to the minus 6, 400. So, 5000 microjoule, but here it is 5800 microjoule. So, there is a difference of these two is your how much, 800 microjoule. The total energy delivered to the 250 kilo ohm resistor is Wr infinity is equal to 0 to infinity Pt dt, that is 0 to infinity just Pt p power is equal to V into I, V is this much, I is equal to this much, this is microjoule, right. Therefore, 0 to infinity 1600 e to the power minus 2t microjoule, so 800 microjoule, right. That means, comparing the result obtained B and C shows 800 microjoule is equal to 5800 minus 5000, so is equal to 800 microjoule. This energy stored in the equivalent capacitor is half, equivalent was 4 microfarad, half C V square, it is 800 microjoule, right. So, this 800 microjoule actually dissipated in the your resistor. So, because this capacitor predicts the terminal behavior of the original series connected capacitor, the energy stored in the equivalent capacitor is the energy delivered to the 250 kilo ohm resistor. So, this problem, this is a good problem for you. So, just when you will get this your video, just have a look that what has been done, and if you understand all this, then you will not face any difficulties of solving this kind of problem. So, thank you very much, we will be back again.